In the last class, we talked about the helical gear problem. And what I'm going to do is I'm going to work out one or two problems on helical gears. And later, I will talk about the bevel gear design. I do not know if I will have time to complete the bevel gear, but depending upon how far we go, if there is some time, I will solve some simple problems on bevel gear, and I will work out a detailed design problem in next class. And then the last gear that is left is worm wheel, and then we move on to internal combustion engines. Okay. So in this problem, power is 15 kilowatts. Pressure angle is 20 degrees. Helix angle is 45 degrees. And pinion RPM is equal to 10,000. This is a very fast pinion. Diameter of the pinion is 80 millimeters. Diameter of the gear is 320 millimeters. Pinion and gear made up with steel. So both materials, both the gear and the pinion, they are made up with steel. And sigma design for steel is 100 Newton per millimeter square. And sigma ES is 618 Newton per millimeter square. So since the gear and the pinion are made up with same material as gear and pinion made of same material, pinion is weaker. So we are going to find out the dimensions of the pinion, because in design we always design the weakest element. P 2 pi nt divided by 60, or Wt is equal to P divided by V multiplied by CS. Service factor is not given, so I'm going to assume service factor is equal to 1. So power is 15 10 to the power 3. Vp is pi. The diameter of the pinion is 80 multiplied by 10,000. So this gives us, can someone calculate this? My answer is 358 newtons. Diameter of the pinion is module times number of teeth on pinion. So number of teeth on pinion is equal to 80 divided by module. Next step is TE. Since it's a helical gear, is equivalent number of teeth, and that is TP divided by cosine cube alpha. So that means 80 divided by m cosine 45 cube, and that becomes 226 divided by m. Now it's a 20-degree stub. So y prime 0.175 minus 814 0.175 0.814 as you know, V is pi d n by 60. It's pi times 80 so 42 meters per second. This is a very high speed, by the way, 42 meters per second. Now to find CV is equal to 0.75 divided by 0.75 plus square root V is 0.104. Please note V is greater than 20 meters per second. Now at this point, I'm going to make an assumption, and you are free to make appropriate assumptions. It's a design problem. So assume B is equal to 12.5 m, which is face width is equal to 12.5 times module. Next step is we use the beam strength equation. WT is equal to B pi m y prime. WT is 358, 100, 0.14, 12.5 m pi times m. Now please understand, in this equation, this is going to be a little bit interesting equation. It's a cubic equation that needs to be solved with trial and error. So you would want to solve this equation using trial and error. Alternatively, if you have programmable calculators, you can just enter this equation and it should be able to give you the answer very quickly. So M is equal to 2.5 millimeters and B is equal to 12.5 times M, 32 millimeters. So this module is face width. Step 2, determination of dynamic load WD, WT plus 21B B times C cosine square alpha WT cosine alpha so 358 plus 21 42 32 287, and you want to be super careful over here. So for this, I'm going to recommend you at this point look at table 28.6 and 28.7. Cosine square 45 plus 358 plus 287 times 42 30, sorry. So once you do this, you are gonna get the value of WD. Now a word of caution. So everyone understood how I got this value of C? If you have any questions, please refer to page 1041. So you will have different values of K. K is equal to 0.107. K is equal to 0.111. K is equal to 0.115. This is for 14.5, for 20 degrees. This is 20 degrees stuff. So what you want to do is you want to use the appropriate value in this equation. C is equal to K times error correction factor divided by 1 divided by EP plus 1 divided by EG. And you will get the value of the dynamic load. The next step of static load. So you have to look at table 28.8, steel. We assume BHN is equal to 400, sigma E is equal to 700 Newton per millimeter square. So WS sigma E right. And this has to be greater than WD, and this is greater than WD for safe. So if you quickly calculate these values, please let me know. So you can tell me what the value is here, and then you can tell me what the value is for WS. The next part is determination of wear load. WW DP P UK Q, since it's an external gear, 2 times velocity ratio divided by velocity ratio plus 1. K is equal to sigma ES square sine phi n divided by 1.4 EP EG. Now to find phi n, tan phi n is equal to tan phi times cosine alpha. This is tan 20 cosine 45. And once you solve this equation, you'll get phi is equal to 14.4. So you need to substitute the values in this equation, and your K will be, so I'll write this down. Then substitute 80 times 32, 2.6, 0.678 divided by cosine square 45. So this answer I calculated 5.5 kilonewtons, that is greater than WD. So at this point, gear design is done. And the next part of the gear design, since in this problem it's not asked, but it's like a shaft design. So to find shaft, what we need to do is we need to look at the forces. And I will do the shaft design in the next problem. But here I just want to give you an idea. So here you're going to have an axial force. You're going to have a radial force. And you're going to have a tangential force. And what you want to do is, if you look at the way the three-dimensional state of stress or three-dimensional loading, FA, FR, gonna have FT. And the total resultant force will be something like this. The resultant force. And in this particular problem, either the configuration is not given or the dimensions are not given. But at the end, what we want to do is we want to find out the moment because of FA, moment because of FT, moment because of FR, and then find out the equivalent torque, and then find the dimension of the shaft diameter. So I will work that problem out in maybe the next Next problem, I work that out. So any questions from online students or any questions from in-person students? Question? Any question? Everyone good? Okay. Next problem. Design a helical gear. P equal to 22 kilowatts. Pinion RPM 1800. Gear RPM 100 and pressure angle phi is 20° full depth. Helix angle 30 degrees. Both gear and pinion made with steel. Face width B is equal to 4 times CP. This is very important. This is circular pitch. Circular pitch is pi times m. Then the gear overhang is 50 millimeter. Tau for shaft is 50 Newton per millimeter square. And in this problem, they have given us value of y, which is 0.154 minus 0.912 divided by CV 350. So step 1, WT P V CS So once you solve this, you are gonna get 9727 divided by n. Now, one thing that please understand that minimum number of teeth on helical gear. So here they say the number of teeth on the gear in P is 24. So in this problem, the minimum number of teeth that are specified But if the number of teeth are not specified, you can just go to design data book and then just find out the minimum number of teeth that are needed so that the interference could be avoided. Equivalent number of teeth is equal to 24 divided by cosine cube 30. This becomes 37. Now what that means is, if this is the helical gear, this is the equivalent spur gear. Y prime 0.154 12 to 9. CV V is pi Tn 60. So pi times m times 24 times 1800 divided by 60. So what that means is you're going to have the velocity in terms of m. So this becomes 135 m. So CV value is 350 plus 135 m. And WT is equal to sigma naught CV times B times pi times m times pi prime. So let's substitute these values. So sigma naught WT is, we already have the equation for WT, 9727 by m. Sigma naught value, we can select the appropriate value for sigma naught. I'm just going to assume this to be 50. So 350 times P is 4 times circular pitch. So once you solve this, you will get the value of m. M is equal to 6 millimeters. And face width B 4 times pi times n 4 times pi times 6, 76. And from here you can find out the velocity, 135 times 6 divided by 5. Oh, just give you in meters. per second. With that, this is for the pinion, and we designed pinion. Please note, pinion is weaker, hence we designed pinion. Next part is the number of teeth on gear is 3 times 24, 72. And now we have to find out the dynamic load. Step 2. Step 3. Step 2. And that is WD equal to WT plus 21V times C cosine square alpha plus WT cosine alpha divided by 21V So side note, WT 9725 divided by M, and M is 6, so this is 1620 newtons. So 1620 plus 21, 13.5, P is 76 multiplied by C multiplied by cosine square. What is the angle? Helix angle 30. Cosine square 30 plus 1620 cosine 30 76. You'll get the value of WD. But to get the value of WD, you need the value of C. And let me, just for my satisfaction, explain you how to get the value of C. So first, you will go to table 28.6. And for 28.6, you will find out the value of E. Depending upon what type of gear it is, whether it's precisely cut or carefully cut, you'll get the appropriate value of E. So, and you would see the value of E actually varies from 0.017 to 0.065. So you can use that, or what you can do is you can also look at the table 28.7 and that should be able to give you the value of E at 0.0. Now for 20 degrees full depth, K is equal to 0.111 for 20-degree full. It's made up with steel. So EP, which is the Young's modulus of pendulum, is equal to the Young's modulus of gear is 200 into 10 raised to power 3 megapascals, which is same as 200 times 10 to the power 3 Newton per millimeter square. So you'll take all this and use the equation for C E K 1 divided by EP plus 1 divided by EG 0.025 0.111. So 2 divided by 200 10 to the power 3, and the value of C we'll get from here. Substitute this value of C in this equation. So if you look at the equation that you have in the back, substitute that value of C in this equation, and that will give you the value of WD. So WD needs to be found out. Next part, step 3. Can someone tell me this value or very quickly? I didn't do these calculations. How much is it? Did you get any answers? There's a lot of calculations, right? That's why. So I will do the easy part. I will just write the equation. You have to do the hard part. You have to find the answer. So step 3. So I'm going to assume BHN 400. Assume sigma E 700 Newton per millimeter square. WS sigma E and this should be greater than WD. Next step is step 4. Determination of wear load, and the equation is WW For this, again, we have to find this value of K, sigma ES square sine phi n 1.4 to find phi n, tan inverse tan 20 cosine 30. And for K, sigma ES value, it's 618. EP and EG is given. So you can find this value and then find WW. WW should be greater than WD. I know I'm going too fast, but this is the third helical gear problem that we are solving. So I hope you are able to keep up. Okay, so at this point, the gear is designed. What we want to do is we want to design the shaft. Step 5. So WT Newton, WA 1620 times tan alpha So let's look at the shaft configuration. This distance is 150. This is WA. If you look at the top view, WT. So I'm going to consider this point A, moment about A. There are two moments, which is first WT times 150, 1620 times 150 Newton millimeter. This is due to WT. Moment at A due to WA. Because 114 is the diameter. That is 67 Newton meter. This becomes 243 Newton meter. So the total moment is square root of 2 square. That becomes 252 Newton meter. As you know, power is 2 pi nt divided by 60. So from here, get the value of torque, then TEQ T square 277 . Solve this and you'll get value of D as 31 millimeter. And last but not least is if you want to draw the housing, is how the housing will look like. There will be a bearing here. Now there is one problem. Let me quickly go through this problem again. So we have to design a helical gear, 22 kilowatts power. The number of pins on pinion are given. RPM is given. Gear RPM is given. So the velocity ratio is 3. The pressure angle is 20 degrees. It's a full depth. and both of these made up with steel. So gear and pinion, same material. So we would design the pinion because pinion is going to be weaker. The face width is 4 times PC. So 4 times pi times m, which is about 12.5. B, the face width is 12.5 times the module. Then the gear overhang in this particular case is given as 150. So this is 150. For shaft design, value of tau is given. So we would follow the process. First, we will find out the WT, assuming service factor is equal to 1. Next part is we will use the beam strength equation. And as you can see, there is M floating around. So the entire equation will be in terms of M. So you can solve this equation and find out the value of M at 6 millimeters. Next step is to determine the dynamic load, and we use the equation for the dynamic load, substitute all the appropriate values, and then to get the value of C, you have to look at the table 28.6 and 28.7, select the value of C, and that should give you the dynamic load. The next part is we need to find out the static load. To find static load, we need to know the structural strength, sigma E, that you can get from the table. For steel, it is assumed to be 600 Newton per millimeter square for the BHN of 400. Please understand, static structural strength, flexural strength depends upon the hardness. So we are going to assume the Brinell hardness number, BHN is equal to 400. And for that, you have sigma E as 700. Then we find the value of WS, and this WS should be greater than WD. Then the last part, we have to find out the wear load. WW is equal to dP times B cube K divided by cosine square alpha. And we substitute the values and then find out the value of WW. And this value of WW should be greater than WD. The last step is shaft design. In this particular problem, the overhang is specified as 150. If it is not specified, then you can assume, but since in this problem, overhang is given to us, we find out the value of WT, which is the tangential load, WA, which is the axial load, find out the moment about A, and then finally find the resultant moment, which is square root of m1 square plus m2 square. Then from power equation, we find out the value of torque. And since the moment and torque, they are perpendicular to each other, we find the equivalent torque. And at the end, we use the equation for torsion and find out the value of diameter. Everyone understood? Any questions here? So next part is if you want to design a gear train. So what that means is you have something like this. So you have two gears in series. You have pinion 1, gear 1. Gear 1 is on the same shaft as pinion 2, and then it is connected to gear 2. Assume this is input. There will be one reduction ratio here. and there will be one reduction ratio here, and this is output. So for an example, if the overall reduction ratio is 9, the overall reduction ratio is the product of VR1 times VR2. And you have a choice. You can assume the first stage reduction is 3, second stage reduction is 3. So if the first stage is 3, second stage is 3. First stage is 4.5, second stage is 2. So you can also have a combination 4.5 times 2. So at the end, the total reduction ratio should be about 9. And usually there are preferred numbers. Preferred numbers, they are something similar to golden ratio, and that dictate what is the optimal reduction ratio. And sometimes what you do is, if you want to design the stages, you will notice what they do is they draw something called as the ray diagrams. And these ray diagrams kind of tell you what would be the reduction ratio in stage 1, what would be the reduction ratio in stage 2, and so on and so forth. So this is a 2-stage gearbox. This is a 2-stage gearbox. But once you decide the velocity ratios for each stages, then you can design these gear trains individually. And if you want to draw the housing, this is how the housing would look like. There will be an input shaft, there will be an output shaft, and this approach is valid whether we are designing the spur gear or whether we are designing the helical gear. And I believe that there is one problem in your quizzes that ask you to do a 2-stage gearbox. So based on the overall reduction ratio, what you want to do is you want to decide the individual velocity ratios, and then you can actually design the individual gears. Okay, with that, we are going to stop here and we'll take a break of 15 minutes. And after we come back, I am going to start the bevel gear designs. Still same. Okay, we'll start in 2 minutes. So any questions on the material discussed so far? Online students, any question? Excellent. Okay, so the next part now is we are going to talk about the bevel gears. 2 minutes. Okay. So the most important thing in spur and helical gears is the shafts need to be parallel. So bevel gears. So whether you consider a spur gear or whether you consider a helical gear, the shafts are parallel to each other. In the case of bevel gears, the shafts are perpendicular to each other. And if both of these gears have the same dimensions, so identical gears, perpendicular to each other, are called miter gears. Now, one classic application of bevel gears is, I do not know if how many of you drive the rear wheel cars. So if you have a rear wheel vehicle, so you have engine up front. So say maybe or a truck. And this power from the engine is delivered to the axle. And here, what you have is, you have something called as the differential. So if you look at the differential, so this is the real axle. And this is how that pumpkin looks like. So then you have the prop shaft that is coming in. The prop shaft will have a bevel gear. And here, there will be two bevel gears. And this is called as the differential. And depending upon the type of configuration you have, you can have a rigid differential, you can have a limited slip differential, and there are various options. So if you look at a rear wheel drive vehicle, you will see this big pumpkin at the end, and that is where that bevel gear assembly is located. Now, once again, the bevel gear are used when the power transmission shafts are perpendicular to each other. And they don't have to be at perpendicular, they can be at some other angle. So at an angle, I'll say. So you can have a bevel gear, which is something like this. So the shafts don't have to be perpendicular. So they can be at some different angles. Please note that these bevel gears are like a cone. So this is like a cone. So what are the most important dimensions, or what is the gear nomenclature? If you have a bevel gear, let's look at how does the bevel gear look like. So this is the gear. This is the pinion. So this is the imaginary friction wheel. And then this angle is the semi-cone angle for gear, and this angle is called semi-cone angle for pinion. So the semi-cone angle for gear and the semi-cone angle for pinion, they have to be equal to the total angle of inclination. So let me draw it properly. It's d theta p and this is theta g. This distance is called as the cone distance. And this is called as the cone center. This is called as the radius of the gear. So this is the diameter of the gear. So the important equations are, and this is called as the cone distance, which is L. Rg, which is equal to the diameter of the gear divided by 2. And I want you to understand that this is actually a right angle triangle. So Rg divided by L is equal to sine theta g. And next thing is Rp is dp divided by 2 and Rp divided by L is equal to sine theta p. And at the end, theta p plus theta g is equal to the angle between shafts. So this could be 90 degrees, it could be 60 degrees, it could be 45 degrees. Now, what are the important proportions of the gear? Now, let me give you the equation for the velocity ratio. So velocity ratio is speed of pinion divided by speed of gear. And that is dg by dp dg by dp, where dg the gear diameter, dp pinion diameter, tg is gear teeth, number of teeth, tp on pinion. And the velocity ratio is dg by dp. I will divide the numerator and denominator by L. So that becomes sine theta g divided by sine theta p. So velocity ratio can be expressed in terms of semi-cone angle. The velocity ratio can also be expressed in terms of the diameters. So for an example, if the question is like this, so this is a question. Say design a bevel gear with total angle, the shaft angle is equal to 70 degrees, velocity ratio is equal to 3. So what that means is theta P plus theta G is equal to 70 degrees. And now you know sine theta P sine theta G is equal to 3. So now you have two unknowns and you have two equations. You can find theta P and theta G. So this is something that you should keep in mind. In case of spur gears or helical gears, you don't have this semicone angle, because if you think about the bevel gear is gear cut on a cone. So you have a cone. So the gears are cut over here. So what are the important proportions? First one is addendum. M is equal to module. To dedendum. 1.2 times module. Clearance 0.2 times M. Working depth thickness and so here is the general process. In the case of helical gear, what we did, when we tried to design, we found out the equivalent number of teeth on the helical gear. So basically the process for the helical gear design is exactly same as the spur gear design. Only thing is we took that helical gear and converted that into an equivalent spur gear. So in this case, to find out the equivalent number of teeth, so if you think about the helical gear, it's in the same plane as the spur gear. But if you look at the bevel gear is actually a three-dimensional structure. So it's actually a 3D gear. So to find out the equivalent number of teeth, what you want to do is you want to map this three-dimensional geometry onto a two-dimensional plane. So what you want to do is you want to map this three-dimensional geometry onto a two-dimensional plane. And this is achieved by a geometric construction known as Treadgold's approximation. So this approximation is called trade gold approximation. So what does this approximation do? This takes three-dimensional geometry of bevel gear and maps this onto two-dimensional geometry to find equivalent number of teeth. So TE is equal to TP divided by cosine theta P. So equivalent number of teeth on the pinion. So these are on pinion. And similarly, if you want to do this for TEG is equal to TG divided by cosine theta G. This is equivalent number of teeth on G. So design steps are similar to the spur gear and helical gear design. So what I'm going to do is I'm going to give you the design recipe, and then we will follow the recipe and solve few problems. So what are the design steps? First, we have to find out WT is P divided by V multiplied by CS. Where P is the power, V is the pitch line velocity, pi dn by 60, and CS is the service factor. WT, the second step, to equate WT is equal to sigma naught times velocity factor times P times pi times y prime, which is the Lewis form factor based on the equivalent number of teeth. But there is one more factor, that is L minus P divided by L. So I'll give you this equation: sigma naught is equal to static stress CV velocity factor, P is face width, and for bevel gears is usually 12 times M to 20 times M. Y prime is Lewis's form factor based on equivalent number of teeth, which is TE. Then L is the cone distance. And cone distance is dp by 2 square plus dg square. CV is 3 divided by 3 plus V for regular gears. And CV 6 for precision gears. The next step, WD is dynamic load. It's the same equation as per gears. As a matter of fact, the tables that we are going to use, they will also be from the per gear. Next step, WS sigma E pi M and to get sigma E from spur gear table 28.8 and WS needs to be greater than WD. The last step is WW, TP, B, Q, K, cosine of theta P. Now please note, semicone angle is included in here. Q, same as velocity ratio, 2 times TEG plus TEP. Please note, in this equation, equivalent number of teeth are used. And WW needs to be greater than WD for the design to be safe. The last part. So before I go any further, any questions about the design steps? Everyone understood everything? Just so first you have power calculation. From power, you'll find the tangential load. Then you'll find out the value of module. Then you will go on to the dynamic load calculation, then the static load and the wear load. The last part is shaft design. So let's look at the configuration. So you can have different configurations of shafts. You can have both shafts cantilevered. You can have one shaft simply supported. So again, depending upon the configuration, you will have to modify this process. But what I'm going to call this, I'm going to call this the gear 1. I'm going to call this gear 2. And at this interface, you're going to have a normal force. You're going to have a radial force. And that there will be a tangential force. So I will give you the equations for Wt is torque divided by the radius of the gear Wn is Wt divided by cosine phi, and last one Wr is Wn sine phi. So Wt, the tangential force, Wn is the normal force, Wr the radial force. And with this, depending upon how the configuration is, step 1 is we have to find reactions. Find maximum bending moment. Then find the equivalent torque. And the last but not least, equate the equation tau GQ G multiplied by R. And then that will give you the diameter of the shaft. So before I attempt the problem, I just want to give you a quick overview. So bevel gears are used when the shafts are at angle. They don't really have to be perpendicular. They can be at some non-perpendicular angle. A classic example of application is using in differential. If two bevel gears are of same size, then they are called as the meter gears. This is how the bevel gear gets assembled. You have a pinion, you have a gear, and the most important thing is, since these gears are cut on a cone, they have something called as the semi-cone angle. So the velocity ratio can be defined in terms of the ratio of the diameters, and it can also be expressed in terms of the ratio of the sine of semi-cone angle. And then moving on, these are the most important dimensions of the bevel gear. And to convert a bevel gear into an equivalent spur gear, we need to use something called as the Treadgold's approximation that does 3D to 2D mapping. And the resultant of this approximation is the equivalent number of teeth is the number of teeth on the bevel gear divided by the cosine of the semi-cone angle. These are the design steps. These design steps are same as the spur gear design, helical gear design. Find Wt, From WT, use the beam strength equation, find out the module, then find out the dynamic load, find out the static load, make sure static load is greater than the dynamic load, find out the wear load, make sure that the wear load is greater than the dynamic load. The last part is you want to design the shaft. And again, the shaft design totally depends upon the configuration. So in this particular configuration, I have shown the gear and the pinion are cantilevered, but they can be simply supported. So depending upon how that shaft is to be designed, you will find the reactions, find maximum bending moment, find the T equivalent, and then find tuition for shaft design. Any questions? So if you do not have any questions, is it okay if I solve the Bevel Gear problem real quick? So this problem, design a Bevel Gear pair power transmission is 35 kilowatts, drive RPM is equal to 1200, compressor RPM (780). It's a 90 degrees bevel. Pinion has 30 number of teeth. Pressure angle phi 14.5. And this problem is slightly different in a sense that here sigma W value is directly given to us, and that is 140 280 divided by 280 plus V. Now, I just want to explain this, what that means. So if you look at sigma W, it's sigma O multiplied by the velocity factor. So what are we doing here? Sigma O is the static strength. With velocity factor, we are trying to make it safer and design it for the fluctuating loads. So this is the velocity factor. In this particular problem, sigma O is given to us and a velocity factor is also given to us. So when we write the equation for the design, sigma W will be replaced by 140 multiplied by 240 divided by 240 V. But this V is given in meters per minute. So for example, if you go to an industry and you have to design a bevel gear, but they have different design standards. The process is the same, but based on their experience, their application, they have come up with this particular velocity factor. And that's what we want to use. The next is Y, 0.124 minus 0.686 divided by TE, where TE is the equivalent number of teeth and B is L by 4. So first let's find out how much is the velocity ratio. Velocity ratio is the output RPM or the pinion RPM divided by the gear RPM. So this is 1.53. The number of teeth on pinion is equal to 30. So number of teeth on gear is equal to velocity ratio multiplied by 30, which is 1.53 times 30, it's about 46. Tan theta p, 1 divided by VR. So theta p is equal to 33 degrees. Theta p plus theta g is equal to 90 degrees. Theta g is equal to 57 degrees. So you can use any equation to find these values. And I just use the tan of semicone angle equation. With this, we have to find out the equivalent number of teeth on pinion, and we have to find out equivalent number of teeth in gear. So T EP is equal to 30 divided by cosine 33, 35.77. TEG is equal to 46. Now, since gear and pinion are of same material, pinion is weaker. So Y prime is 0.124, 0.686 TEP, 0.124, so we are going to design pinion. WT equal to P divided by V multiplied by service factor. So we are designing pinion. So to find velocity, it's pi times diameter of pinion times 6 multiplied by n, which is 1200 divided by 60. So pi times m times 30, 200 by 60. So you will have to substitute this value over here. Service factor is 1. So once you solve this, everything will be in terms of m, and my answer is 18.6 by m. Step 2. WT is equal to sigma naught times, sorry, this is sigma W. P times pi times m times L minus P divided by L. In this problem, sigma W value is already given to us, which is 140, 280 divided by 280 plus P. 140 the only difference here is for V, it has to be pi dn, because this velocity has to be in meters per minute. So this would be pi 30 times m n 1200 multiplied by b multiplied by pi multiplied by m multiplied by L by B ratio is 4. That is given. So this becomes 0.75. The next thing is B by M ratio is also given. So this is from the data book. So substitute this value and you get 140 multiplied by 280 plus pi and once you solve this equation using trial and error, you will get the value of m. These are the important dimensions. So next step, step 3. Is we have to find out WD. WD is WT plus 21V P times C plus WT 21V plus square root of P times C plus WT. So this is 23, 21 plus 21, 15, 96, 618 plus 2321 divided by and you will see in this case WD you will get something like 36 kilonewtons. It's quite high. Actually, can you check? Can somebody tell me this value real quick? Then WS sigma E times B times pi times M times Y. I'm going to assume sigma E is equal to 490 Newton per millimeter square for BHN of 240. If you want to go BHN 400, you can go all the way to sigma E is equal to 600 Newton per millimeter square. So substitute the value of sigma E. So for example, 490 times 96 times pi times M times Y. So I got this at 36 kilonewton, but it seems high, so please check this answer. It is 124. So since WS, WD, design safe. The next step is WW is equal to dP B times Q times K Q 2 TEG divided by TEG plus TP. Please note, these are equivalent number of teeth. And then substitute so K value comes from sigma ES sine phi with the value of K, and then you want to make sure that this value is greater than WD. For some reason, if WW is less than WD, that can happen. Design needs to be reiterated. In that case, you can use a higher value of BHN as 400, and for that sigma ES will be 1050, and then your value of WW will be significantly higher. So please work out the problem and then make sure that my numbers match with your numbers. But at any time, for some reason, if the design is failing and your calculations are correct, what you can do is you can go back and reiterate the numbers and actually make that design safe. The easiest way to modify a design is by changing the material or changing the hardness, rather than going and changing the dimensions, which is a perfectly valid option. It's just better to change the material. Last part is shaft design. So I'm going to have this type of configuration. This is just, I'm assuming. So WT equal to 2321 that we already found. Wn is WT divided by cosine phi, which is 2321 divided by cosine 14.5. WR is equal to 2321 sine of 14.5, so 581. So bending moment because of the tangential load, and I'm just going to assume this dimension because the center distance between the bearings is not given. Equal to WT times L divided by 4, because this is simply supported. So PM WR times L by 4, 581. And since we have these bending moments that are perpendicular to each other, we want to find out the total bending moment. So this answer is 119 Newton meter. Then TEQ is equal to square root of PM total square plus T square. And T is WT multiplied by 240 by 2, which is 278 Newton meter. So this answer is 119 square plus 278 square. That gives me 303 Newton meter. And next part is TEQ divided by pi by 32 t to the power 4 t by 2 equal to tau. I'm going to assume 50 pi by 32 t to the power 4 t by 2. Solve this equation. My answer is d is equal to 50 millimeter. Everyone followed so far? Any questions? Oops, this is what I was worried about. So PowerPoint crashes on iOS. Okay, finally. Okay. So we covered significant amount of material today. What is open? Helical gear. Oh. It's not right. Anyway, so we have covered the bevel gear design. So we will stop here and I will see if I can upload the notes. For some reason, if the notes disappeared, then you have to unfortunately follow through the PowerPoint, I mean the class discussion, and then follow the notes. But I'm going to stop here and